Hi, today we're going to finish with option D, higher level, talking a little bit about extraction and purification methods and methods of detecting particular compounds using different spectroscopic methods. All right, so for extraction and purification, it really is just more of common sense. Let's talk a little bit about this. When we make a chemical, a lot of the times we're going to be using this chemical and we're going to be making it in some type of organic solvent. Okay, now in order to isolate the solvent, we need to bring it out of solution. We need to precipitate it. One of the methods that we use to do this is to actually put this pour into the solution ice water. All right, ice water will change the polarity of the solvent. All right, and by being colder, it allows less of the solid to be dissolved in your solvent, and so normally this will cause precipitation to take place. If that is not the case, if something is too soluble, one of the other things that we can do is, if we have it in an aqueous solution, if we can, and I'm going to make this image a little bit larger, just a second. All right, what we can do is use something that is called the separatory funnel. All right, so we put our aqueous layer that contains our compound. If that compound is an organic compound, a medicine of some type, it's going to be probably more soluble in a non-polar organic solvent. All right, so we can add the non-organic solvent in here, the non-polar solvent. All right, and that will create a two-layer system. One that will have the aqueous layer and normally lower density organic solvent on the top. If you use a halogenated solvent, something like dichloromethane or chloroform, the organic solvent will be in the bottom because it's denser than water. Right? But if you shake your mixture, and you're going to vent it by not pointing towards anybody, just in case to remove any excess gas or etc. forms, you will be able to literally dissolve your solution that was in the aqueous layer into the organic layer, which is more nonpolar. You can then pour out into a container your one of the layers, separate one layer from the other, recover the layer that you want, whether it's the aqueous layer or the organic layer, normally the organic layer, and then you can evaporate that solvent and regain your actual chemical that way. Now, that's all wonderful, but it will not give you a pure substance because you may have taken with it some other organic materials that were there. So we have isolated it, we have removed and taken the organic substance that we want from our synthesis, but we need to purify it again. So one of the processes for purification, the first one that we're going to talk about is the idea of recrystallization. Recrystallization is when you are going to take that solid that you precipitated out, or that you have evaporated the solvent away from and has any impurities, and you're going to redissolve it in some warm solvent. All right, now you want to do that so all the impurities and all of the compound dissolves, but you want to do that in a minimal amount of solvent. As you let the solvent cool down, and you can use an ice water bath, you put your container, your flask into the ice water to allow for the your solid substance, your compound, to precipitate out of the solution. Now, you may not recover all of it, but that's okay. What you're going to recover is going to be crystalline, it's going to be clean, and it's going to be not have any of the impurities, because the impurities tend to stay in solution because there's less of them. All right, while your compound will precipitate out. That is recrystallization. So you had something solid, you dissolve it in minimal amount of solvent, warm solvent, and then you let it cool down until it precipitates, comes back out of solution. A second method that you can use is using chromatography. You're going to have some type of stationary phase, all right, something like a silica gel or a paper. All right, and you're going to put your substance onto that substance. All right, it could be the column as well, and you're going to pass a solvent. The solvent will move, all right, the chemical and separate the chemicals depending on the way, if you have multiple chemicals in there, in the way that they interact with the solvent, which one's more soluble depending on polarity, and you can be able to have different what are called retention times for the solvents, for the compounds. And so depending on how they separate, then you can peel off that piece that has the chemical that you desire. Okay, and you can do this in a column as well. So if you have it in a tube that is filled with a particular substance, you can have some of it kind of move with your solvent. The other part is remaining at the top, and so you can then take out your column and just remove the parts when you have separated one product from another, or one product from the impurities. All right. The final way that we can do this is what is called fractional distillation. Now, when we talk about fractional distillation, we need to have what is called a fractional distillation column, such as this. All right. What we are going to be doing is we're going to heat our substance, normally some type of liquid, all right, and we're going to separate it from the other liquids in the mixture depending on its boiling point. All right. So as the substance heats up, the vapor is going to go up the column. Because the temperature is lower up the column, only the lower boiling point substance will stay in the gas phase. But what's going to happen is it's going to recondense, and it's going to evaporate and recondense and evaporate again and recondense and evaporate. And slowly you are going to get only the lower boiling point in the upper part of the column, which will then be condensed and collected in a separate container. As you see the different fractions coming out, as you see the first lower boiling point substance coming out, and when it stops, you can change your collection flask and get the next fraction and the next fraction depending on separating by their boiling points. All right. Now let me make a quick stop. The reason that fractional distillation works is because of something that is called Raoult's law. All right. The vapor pressure of a substance, all right, depends on the intermolecular forces present in that substance. All right. So if we have a gas in equilibrium above a particular liquid, the percentage, all right, composition of that gas is going to depend on the vapor pressure of the substance. All right. So if we have, for example, a mixture that is 50-50 between these two substances, octane and hexane, all right, hexane has a lower boiling point, a higher vapor pressure than, and you can see it here, here's the vapor pressure of pure hexane, here's the vapor pressure of pure octane. If you have a 50-50 mixture, the gas will actually contain more hexane, all right, than it contains octane, because octane has a lower vapor pressure. It produces less gas at any given temperature. Okay, and so you are taking advantage of the fact that what you are going to recondense every single time is the gas. So it goes up at 50-50, let's say, and then because of that 50-50 initially, your gas actually is going to be maybe 70% hexane, 30% octane. That recondenses. Now you're at 70-30. When you evaporate that again in the fractional distillation process, it may go to 90-10. When you recondense that, maybe goes to 95-5, etc., etc. So the more stages of condensation and re-evaporation that you have in a fractional distillation column, the purer that you can get that substance, the bigger and better separation that you can have. All right. So the general equation that we use for this, all right, is this idea that the vapor pressure of a gas A is equal to the mole fraction, and the mole fraction is literally the number of moles of that particular substance divided by the total number of moles in the liquid, all right, times the vapor pressure of that pure liquid that you're talking about. All right, so this allows us to make these separations. Now in the IB, all you need to basically know is that this happens because of Raoult's law, that there is this equation, but you will not be really required to calculate with this. We will talk a little bit more about this directly in class when we can actually have some answers and I can really show you a little bit more about this. But I just wanted to put it up here for in terms of completion, in terms of what we do for isolation and purification. Okay. Now, when we talk about detection, there are many types of chemicals that we want to see how, if they're present in somebody's body, in their blood stream, or in a particular chemical, in a particular nutritional supplement, etc., etc. One of them, the ones that we are very concerned about, are anabolic steroids. All right, anabolic steroids have this particular skeleton that is based on the skeleton of cholesterol. All right, now this includes many many hormones, all right, like testosterone, all right, but it also has a number of different artificial anabolic steroids, like nandrolone or stanozolol. All right, those are particular enhancement drugs that help build muscle, and if they are present in your body, they mean that you have been taking steroids, and of course that would disqualify you from many of the sports competitions that we have around the world, including cycling or swimming. Some others are a little bit less eager or less stringent in their testing for this. Now, how do we test for these substances? Well, it's very straightforward. One of the methods that we use is something that is called HPLC, which means high performance liquid chromatography. So chromatography, again, we're going to separate substances by their retention time, how their polarities, etc., etc. And so if we know where a particular, we can test what the retention time should be for a particular drug, and then we pass a sample that we have isolated from somebody's blood, and if it contains a peak at that particular retention time, we know that that drug is present. And so this is one of the ways in which this is tested. This is a relatively straightforward idea. We are going to center more on the detection of ethanol, all right, and talking a little bit about ethanol. And ethanol is a depressant drug. When we talk about depressant, means it actually lowers the activity of the central nervous system, all right, and in low dose it causes, relaxation, decreased inhibition. People become more talkative because of the decreased inhibition, all right. It has some anti-clotting effects as a side effect. It improves circulation because it causes relaxation of blood vessels, all right. But if you abuse alcohol, all right, in short term, you can have loss of self-restraint. You can become violent because of that loosened inhibitions. You're more likely to risk take because your reasoning is somewhat impaired. Your concentration is lower, your reflexes are slower, and your response time is also slower. You can have a loss of coordination and balance. In higher amounts, it can cause vomiting, dehydration, and extreme amounts in one take can cause alcohol poisoning, and it can lead to coma or death. All right. If you have a chronic dependence on alcohol or use of alcohol, you can develop liver disease. It can also cause heart and coronary disease because it causes the hardening of the blood vessels, otherwise known as osteosclerosis. All right. It also can, because of that, can cause high blood pressure and can cause several different diseases in your liver, including cirrhosis and cancer. If you are drink during pregnancy, it can cause fetal alcohol syndrome. And because this continues to act and attack your brain, chronic use of alcohol, chronic abuse of alcohol can cause permanent brain damage. And this is actually something that we can see. We have seen people when they become, when they develop alcoholism, you can see people having tremors in their hands. This has to do with actual damages of the motor neurons. All right. Alcohol is particularly has increased effects or synergistic effects with some different drugs. With aspirin, it can because it dissolves the aspirin more and it allows it to go through the different mucus layers, it can actually cause stomach bleeding. With antidepressant drugs, all right, or other depressant drugs, it can actually cause increased sedation. So like if we're talking about mixing it with opiates or things like that, this will actually can cause depression of your breathing. It can actually cause significantly more of those sedative effects, all right? With tobacco or other smoke, it can increase the risk of cancer because it solubilizes carcinogenic compounds more, and so therefore they're going to be intaken more easily. And with other drugs, including THC, it can cause some liver toxicity because, of course, some of these drugs, this is where your body can break down drugs. It's in your liver, and so if you're putting more and they dissolve more readily, you can be attacking that more. All right, so that's basically how alcohol works. Now let's talk about detection of alcohol. All right, detection of alcohol is normally done through different methods. All right, method number one is the breathalyzer. If you have alcohol in your bloodstream, all right, what's at the other side of your alveoli is your bloodstream. So if you breathe out, okay, some of the ethanol that is in your blood will actually pass through the alveoli into your exhaled air. All right, and it can be measured. So if you have just the common chemical breathalyzer, all right, you would have a sample of potassium dichromate, which is orange. If you blow into it, as we remember from organic chemistry, this will cause the dichromate to oxidize the alcohol, and it itself, the dichromate, becomes reduced, and it gets reduced to chromium 3+, and so it will change from orange to green. All right, so this is the kind of the reaction, the typical reaction that we have for the oxidation of ethanol through with dichromate all the way down to ethanoic acid. All right, it could have been oxidized to the aldehyde, but either way, the color change is still going to be from orange to green. Okay. The second type of method that we can use is we can isolate the alcohol that is present in your bloodstream. We can take a sample of blood or a sample of urine and actually separate the alcohol and then burn that alcohol in a particular, what is called a fuel cell, to very exactly measure the amount of alcohol that was in that sample, and therefore we can get the concentration. This is very accurate, but costly and difficult to do, so normally we use other methods rather than the fuel cell, even though it's the most accurate method there is. All right. The third method that we use is by using the IR. All right. Now, if you exhale, that gas that you exhale will contain ethanol. Now, it will also contain water. So we are not going to use the OH stretch because the OH stretch is present both in ethanol, but it's present in water as well. So that is going to be useless. But what you breathe out should not have any organic compounds. It should just be carbon dioxide. It should be water. All right. But if we have a CH stretch in there, it's very indicative that you have some alcohol that has evaporated, passed through the membrane between your alveoli and the bloodstream, and come out in your breath. And so that is a way that we can actually use to measure, and depending on the strength of that peak, all right, of that stretch for the CH, we can then measure the amount of ethanol present in your breath. Another method that is used, and it's actually even better, is using gas chromatography. Now, if you take a sample and you heat it up, this is going to evaporate the different components of your blood or the different components in your urine, all right, including any ethanol that may be present. Now, if this gas is passed through a gas chromatography column, it will separate depending on boiling point. And so if we know where ethanol is, we know where the boiling point of ethanol should be, and so we can actually measure the height of the peak in order to calculate what the concentration of the ethanol is. In order to have a good comparison, we tend to put a small sample of propanol, which will appear in a different region. But by knowing how much propanol we can measure that area and use that as terms of comparison to calculate the concentration of the alcohol in your blood or urine, and therefore be able to tell how much was present in that sample. Now, all of this is ways of detecting. Now, it's all a puzzle. All right, we have to be looking at all the different portions. We can do mass spectroscopy, we can do IR, we can do NMR. So, for example, here are all the different samples that you would have for a sample of ethanol. All right, and if we look at this, and I'm going to be on the screen in a moment, but we can see we have an OH peak here. All right, so that's a nice indicator. And how do we know that this is the OH? We're going to go and look in our data booklet. Our data booklet on table 26, we have the infrared spectra. All right. In table 27, we have the NMR data. And on table 28, we have how to help us analyze mass spectra data. All right. And so we know that we have an OH. So that's a strong indicator. Now, if we look at the NMR spectrum, okay, we have something that has an integration of 3 and has 3 peaks. So that means that that 3 is next to a CH2. And then there is something that has an integration of 2, which has 4 peaks, which means that it's next to a CH3. And then a single peak with an integration of 1. So the indication is that this would be the CH3 next to a CH2. And this is a CH2 next to a CH3. And then this is likely to be the H in the hydroxyl group. All right? Finally, the mass spectrum helps us figure this out completely. The parent peak is at 46, okay, which is the mass spectrum, the molar mass of ethanol. But the big difference between this peak and over here, which is at 31, the difference there is 15. It's a loss of 15, which represents a CH3. All right? Losing 15 is a clear indication that we have a CH3 group. All right? And we may say, okay, well, but what else could we have lost? Anything else that we have there? We have a 45, meaning that we could have lost an H from the OH, okay? And then there are a couple of other places where we can have some other indications. So in this particular case, the mass spectrum is not as helpful, but the IR and the NMR have definitely sealed the fate of this. And we have that possibility of a CH3 being lost, which is also part of the structure. So we can confidently say that we have ethanol and nothing else in this particular sample. All right. There are other samples that we can have here, over here, and I don't think you can see it very well. The formula says C4H6O. Let me just make sure that I read it correctly. Sorry, C4H8CO2. C4H8O2. All right. So now let's break this down. Let's look at the HNMR. All right. Again, we have 3 hydrogens next to a CH2. So this is probably this. Then we have 3 hydrogens that are a singlet. We don't know what that is going to be. And then we have 2 hydrogens in a set of 4. So that's going to be next to a CH3. So we have this CH2, CH3. All right. And this, because of the integration, this must be some type of isolated methyl group. Now, if we look at our data booklet, because it's all the way at 3.7 or somewhere around there, we must think that it has to be something that is connected to a C double O CH3. All right. So this is a CH3 that is isolated. by connection to something that has this particular structure. All right? We're like, okay, so what could it be? Now let's look at the mass spectrum. Let's look at some of the data that we have there. All right, if we look at that, this peak over here is about 88. And this peak that shows up here is at 59, and this one is at 57. This difference here is a difference of 29. It's the loss of an ethyl group. All right, we can look at that in table 28. This difference here is a loss of 31. A loss of 31 tends to indicate the loss of a methoxy group. And so this kind of complements our idea that this CH3 is isolated from the rest by some type of CO bond. All right? And finally, we can come over here to the IR spectrum. We see a very strong C double bond O stretch. We see what is probably a C single bond O, but we're not 100% sure. And no OH, so there's no alcohol possible in this case. So if we have this structure, all right, we start thinking about what are the things that we have, and from the NMR spectrum, almost exclusively, we can get the formula or the structure of this compound. It must be a CH3, CH2, C double bond O, O, CH3. All right? It's the only compound that actually matches the information that we have. Lastly, we're going to test another one. All right? This formula is C3H6O. Well, let's look at what we have. Well, we don't have an alcohol. It does not look like an alcohol. It looks kind of flat and small. So that's not neither an alcohol nor an amine. There is no nitrogen in the compound. All right, but we do have around 1700 a nice stretch. So this is likely to be a C double bond O stretch. All right, and again, we'll look in our table 26 for finding that value. We'll look at the mass spectrum. We have a value here at 58. And we have value here at 43. A difference of 15. So there's a loss of a methyl group. All right? Nothing much more that is particularly relevant there. And then we have a very, very simple NMR spectrum. It's a single peak. All right? And it's around position 2. If we look at our NMR peak and around position 2, that could be, all right, a CH2 that's connected to a C with 2 oxygens, or a C connected, double bonded to an oxygen. Since there is only one oxygen, we're going to say that this is going to be some CH next to a double bond oxygen. Well, given the information that we have and the fact that we can lose one methyl group and that we have 3 carbons, 6 hydrogens, and 1 oxygen, the options that we have really available to us are very limited. This propanone is a compound that would produce this spectra. Why? This methyl group is identical to that methyl group, therefore they're in a single environment and create one peak. Because they do not have any hydrogens in the adjacent carbon, they become a singlet. All right? There is no way of knowing the integration because integrations are relative to other things. There's only one peak, so we don't know anything about that. But this seems to fit all the particular information that we have. And voila, this is it. This is how we use spectra in order to detect and deduce the identity of different compounds based on the chemical formula and the different spectra. All right, thank you very much, and that is the end of option D.